Hi everyone! Today we're going to explore how Java interfaces are used in real-world applications, along with some practical examples. This slide outlines the content of the video. First, we'll introduce Java interfaces with a simple animal example. Then we'll explain 3 key benefits of using interfaces, each demonstrated with a real-world case. Finally, 4 real-world example demos will be discussed. They are Animal Interface Example, Logger Interface Example, Payment System Interface Example, and Event Handling Example.
Let's begin by exploring what is an interface in Java.
An interface acts as a contract. It defines method signatures without providing their implementation. Classes use the implements keyword to adopt and define the methods of an interface. Interfaces support abstraction and allow a form of multiple inheritance in Java.
Now we'll explore a simple animal interface example to understand how Java interfaces work.
We begin with the animal interface, which defines a single method, makeSound. This sets a contract. Any class implementing animal must provide its own version of makeSound. The dog class implements the animal interface. It provides the actual behavior for makeSound, printing woof to the console. This shows how a specific class can fulfill the interface contract with unique behavior. In the basic demo class, we create a dog object and call its makeSound method. The output is woof. This demonstrates how an interface ensures consistency while allowing different classes to define their own behavior. This simple example shows the power of interfaces, defining a common contract for multiple. In this page, I will explain 3 key benefits of using interfaces in Java, promoting loose coupling, ensuring consistency. First, interfaces promote loose coupling. This means that classes in a program depend on abstractions, in other words, interfaces, rather than concrete implementations. By doing this, we reduce direct dependencies between classes, making the system more flexible and easier to maintain. We begin with the payment processor interface, which defines a single method, pay, double amount. This interface acts as a contract. Any payment class must provide its own implementation of how a payment is processed. The credit card payment class implements the payment processor interface. Its pay method prints a message showing the amount paid using a credit card. This represents one type of payment method. The PayPal payment class also implements the payment processor interface. Its pay method prints a message showing the amount paid using PayPal. This demonstrates how different classes can implement the same interface in their own way. The checkout class depends on the payment processor interface, not on a specific payment type. We provide a payment processor implementation through its constructor. When complete order is called, it delegates the payment to whichever implementation was passed in. In the Payment with Interface class, we see this in action. First, we create a checkout with a credit card payment and complete an order of $101.0. Then, we create another checkout with a PayPal payment and complete an order of $50. Each payment is processed correctly according to the chosen method. This example demonstrates important software design principles. Polymorphism. Different payment methods share the same interface but behave differently. Loose coupling. Checkout does not depend on a specific payment class, only on the interface. Flexibility and extensibility.
We can easily add new payment methods like Apple Pay or Google Pay without modifying the checkout class. By using interfaces, we create flexible and maintainable code that can adapt to new requirements with minimal changes.
Second, interfaces ensure consistency across classes. When multiple classes implement the same interface, they are guaranteed to have the same set of methods. Even though the implementations may differ, the structure remains consistent, making it easier to work with different classes in a unified way. We start with the vehicle interface, which defines two methods, start engine and stop engine. An interface is like a contract. Any class that implements vehicle must provide code for these methods. Next, we have the car class implementing vehicle. It provides its own version of start engine and stop engine, printing car engine started and car engine stopped. This is how a specific class fulfills the interface contract with behavior unique to a car. Similarly, the bike class also implements vehicle. Its start engine and stop engine methods print bike engine started and bike engine stopped, showing unique behavior for a bike. In the vehicle demo class, we create a vehicle reference called myVehicle. First, we assign it to a bike object and call start engine and stop engine. The bike's behavior runs. Then, we assign the same reference to a car object and the car's behavior runs instead. This example demonstrates polymorphism. The same interface reference can work with different vehicle types, each performing its own specific actions while following a common interface. We start with the vehicle interface, which defines two methods, start engine and Finally, interfaces enhance testability and flexibility. During testing, we can swap real implementations with mock versions without changing the dependent code. This allows us to isolate parts of the system, test them independently, and achieve faster, more reliable testing. In summary, interfaces help us design better software by promoting loose coupling, ensuring consistency, and enhancing both testability and flexibility. We start with the data service interface, which defines a single method, fetch data. This interface sets a contract. Any class implementing it must provide a way to fetch data. The database service class implements data service. It represents a real-world data source, such as a database, and returns actual data when fetch data is called. The mock data service class also implements data service. However, instead of fetching real data, it returns test data. This is useful for testing without relying on a real database. The data processor class depends on the data service interface, not a specific implementation. We inject a data service object through its constructor and call process, which prints the fetched data. In data processor demo, we create a mock data service and pass it to data processor. When we call process, it prints test data. This shows how we can swap implementations easily using interfaces, making testing simple and flexible. This example demonstrates two important concepts. Dependency injection, we provide the service to the processor instead of hard-coding it. And polymorphism and testability. The same data processor works with any data service implementation, real or mock. Finally, I will walk you through some real-world examples of how interfaces are applied in Java. We'll look at three cases: the animal interface, the logger interface, and event handling with interfaces. In the first example, we define an animal interface. Both dog and bird implement the same methods, but in their own way. A dog barks and runs while a bird tweets and flies. This shows how interfaces allow consistency with different implementations. We start with the animal interface, which defines two abstract methods, make sound and move. This interface acts as a contract. Any class that implements animal must provide code for both methods. The bird class implements the animal interface. Its make sound method prints bird says tweet tweet, and its move method prints bird flies in the sky. This shows how a specific class fulfills the interface with behavior unique to a bird. Similarly, the dog class also implements animal. Its make sound prints woof woof, and its move prints dog runs on four legs. Again, the interface ensures consistency while allowing each animal to behave differently. In the animal demo class, we create two animal references, one for a dog and one for a bird. We call make sound and move on each. The methods executed correspond to the actual object, dog or bird. This demonstrates polymorphism. The same interface reference can work with different types of animals, each performing its own behavior while following the same contract. In the logger example, we define a logger interface with methods for info, warning, and error messages. A console logger shows logs on screen, while a file logger saves them to disk. This demonstrates loose coupling. We can swap one for the other without modifying the dependent code. We start with the logger interface, which defines three methods: log info, log warning, and log error. This interface acts as a contract for logging messages at different levels: informational, warning, and error. The console logger class implements logger. It prints messages directly to the console with appropriate tags: info, warning, and error. This is useful for real-time logging during development or debugging. The file logger class also implements logger, but writes messages to a file instead of the console. It uses a file path provided in the constructor and appends log messages with timestamps. This is ideal for production environments where logs need to be stored persistently. In the logger demo class, we create a logger reference. First, we assign it to console logger and log an info, warning, and error message, all printed to the console. Then we switch the reference to a file logger and log more messages. This time they are written to a file named app.log. This example demonstrates polymorphism. The same logger reference works with different implementations. Flexibility, we can easily switch from console logging to file logging without changing the logging mechanism. Separation of concerns, the application logic does not depend on the logging mechanism. And extensibility, we can add new logger types like network or database loggers with minimal changes. In the event handling example, we have an on-click listener interface. A button can use it to handle clicks. By registering different listeners, we can define unique actions for different buttons, improving flexibility and reusability. We start with the on-click interface, which defines a single method, onClick. This interface acts as a contract for handling click events. Any class implementing it must provide behavior for what happens when a button is clicked. The button class represents a clickable button. It has a name and an onClicker reference. We can register a listener using the setOnClicker method. When the click method is called, it prints that the button was clicked and then triggers the listener's onClick method if it is set. In the event listener demo class, we create a button object named submit. We register an event handler using a lambda expression. This lambda defines what should happen when the button is clicked. In this case, it prints handling click event for submit. Finally, we simulate the user clicking the button by calling mybutton.click. The program first prints that the button was clicked, then calls the lambda, printing the handling message. This demonstrates how events and callbacks work in Java.
using interfaces, lambda expressions, and decoupling. The button doesn't need to know what happens when it's clicked. It just notifies the listener.